Okay, let's imagine a very idealized source and detector setup. And we have this source with some source strength S naught and a phantom down here to represent where the patient would be lying on the couch. We'll start by assuming the source is an isotropic emitting point source, but this line will indicate the central axis of the emission in the direction of the patient. The distance separating them is an important determinant of the penumbra effect, and it has a special name, the source to surface distance, or SSD. Let me write that down. Source to surface distance. Yep. SSD. It'll be a little clearer how SSD affects the beam penumbra if I redraw this phantom as a straight line. Our isotropic emitter is hitting each point on this line, but the intensity decreases as we get farther away from the central axis because the distances to those points are greater. Very far off axis, the contribution to dose on that lateral line from this point source is much smaller because the lessened intensity leads to lessened exposure, less ion pair production. Now, the decrease is in proportion to the square of that distance. Or we call this the inverse square law. Inverse square law. Right. But we also have other ways of reducing the radiation intensity outside of the edges of this field that we want. For example, we can still use a relatively isotropic source for therapy like cobalt 60, but we need to occlude or collimate those extraneous emissions with some highly attenuating material like tungsten. So let's just assume for now that these collimator blocks are perfectly attenuating and neglecting scatter effects. There's just no radiation incident outside of those edges of our field at this level. So let me demarcate those edges. Now, I'm going to draw a percent depth dose curve, PDD, to show how the dose is distributed laterally at this line. So PDD, that's the unit is percentage of the maximum dose. And that maximum dose 100% mark is up here, 0 down here. And this horizontal axis is the lateral distance from the central axis in centimeters. Centimeters. Okay. Centimeters. Now, let's say this is a 10 by 10 centimeter squared field. And our PDD is going to look kind of like this. Kind of like this. Let me correct that. There we go. All right, I fixed it. It's a step function. But let's see what happens when we alter some of our parameters. So what if we move this source farther up into the beam head? So there's a greater distance between it and the collimators. That distance is called the source to diaphragm distance. Diaphragm has to do with the gap between the collimators. So that's the source to diaphragm distance, or SDD. So yeah, let me just note that here. The diaphragm is related to the collimators. So now, with a point source, this doesn't really change much, but we don't really have point sources. We have beams with finite lateral extent. And that means that the little elementary sources spread out across that lateral size are going to have different distances to the points on the surface of our patient. And the contribution of each elementary source to the dose at each of those points will diminish. The result of this is that there's gonna be a smooth, rather than immediate, fall off in the lateral dose distribution on that surface, depending on the size of the source, as well as the field size prescribed by the collimator diaphragm. So if we widen it, more points on that finite source can emit and reach points on the surface farther laterally than the edges of our field. So the PDD will now have this smooth, continuous deformation at the edges, rather than that black and white difference between in-field and out-of-field regions. And this new boundary region specifically is what we call the penumbra. Let me clean up a little now. So what are some other parameters that affect the shape of that penumbra? Well, one is the geometric size and shape of the source. If you have more elementary point sources distributed in the lateral direction, the ones closer to the edges of that source will be able to irradiate farther out past the edges of the field. And assuming we maintain our symmetry here, what we're going to see in the PDD is a broadened fall-off region on both sides. So let me draw that with orange here, showing how the extent increases at the lower dose isopoints, those being points on the PDD where the dose value is at the same fraction of the maximum dose. In particular, the isodose values we tend to use to quantitatively distinguish between different penumbras are the 80% and 20% marks. On each side of the field, we can say that the width of the penumbra, we can call it W, is the lateral distance between those points. So to recap, we've seen that the width is proportional geometrically to the source size, and it's also proportional directly to the SSD, or source to surface distance. But it's actually inversely proportional to the SDD. So the farther along the beam line you place the collimator diaphragm, the thinner will be the geometric penumbra. And that's what we'll call this one aspect of the penumbra effect. So let me write that here. Let's see, geometric penumbra. But there are other factors that contribute to the penumbra effect, and the next one we'll talk about is the transmission penumbra. So in addition to the effects of various distances and angles, a real problem we have to consider with photon beams is that their interactions in matter are probabilistic, meaning that some fraction of the intensity of an incident beam however small, will inevitably, in all likelihood, leak out through your shielding material, including the collimators, and pass through regions where you would really prefer it didn't, such as the outskirts of your field. So I'll just be drawing a new setup here with a small finite photon source collimated with these crudely rectangular blocks of, say, tungsten, and raised by some SSD distance along this central axis above a flat lateral surface. And as I begin to draw the lines at the edges of the beam, including through the collimator blocks, what we'll see is that some of these lines have to pass through different thicknesses of the collimator material. Let's call that distance, we can call that distance x. Let's see, call that distance x. And what do we know about photon interactions and distance? Well, they obey the Beer-Lambert law, or just Beer's law, or also known as the law of exponential attenuation, which tells us that the initial photon intensity in units of photons per unit time per unit area, I naught, at the point incident on some new intervening medium, will be reduced at increasing depths of penetration into that medium exponentially with a rate constant mu, which we call the linear attenuation coefficient. So let me draw another little PDD down here and think through what effect this will have on the shape of the penumbra. So if this time we allow some of the beam to pass through these collimators and hit outside the edges of the field, the differential contribution from a point in the source will be further lowered, not only by the inverse square law, but also exponentially by the length of the sector over which it traverses the collimator. So what we're going to see is actually a very similar, continuous, smooth decline, but with additional contributions due to this previously unaccounted transmission. And so there have been some techniques developed in collimator design to mitigate the effect this has on the dose uniformity of the field, including the machining of collimator blocks so that they have this angled edge, and this way there's a much more abrupt change in intensity between the unattenuated inner field edge and the part that just begins to be attenuated by the suddenly large thickness farther out. And another technique is making collimator leaves with rounded edges so that the difference in thickness doesn't change as dramatically as the beam fans out. And this has the additional advantage of using less material, which can make moving the leaves around to conform to different shapes in IMRT and VMAT delivery less strenuous on the actuators. So that's transmission penumbra. And there are some other factors that contribute to this smearing out of the beam. The main factor that we could talk about next is the loss of lateral electronic equilibrium due to the photons scattered out of the beam, producing a gradient of energetic electrons in that penumbra region. But for now, we can just summarize that higher photon energy is a principal variable in both of these factors because it leads to more scattering as well as more transmission through the collimators. But it's important to note that this is dependent on the collimator material characteristics, such as attenuation coefficients, as we've seen. Now let's review what we've learned. The penumbra is the region at the lateral edge of the beam where dose falls off continuously. And two big contributors to this effect are the geometric penumbra and the transmission penumbra. In geometric penumbra, the relevant parameters are source size, source to surface distance, or SSD, and source to diaphragm, or collimator distance, SDD. And we can extend that SSD with the depth into the target to get this approximate width equation given by Kahn's radiation therapy physics, chapter 4. The transmission penumbra, on the other hand, is caused by differential attenuation in the intervening material of the collimator, and higher photon energy leads to greater penetration and thus a broader lateral beam profile. And finally, I'd like you to consider these questions to test your understanding of the concepts underlying penumbra. First, does geometric penumbra depend more heavily on SSD or SDD? And how do you think the answer might influence the design of a LINAC and patient positioning? Second, based on this graph to the right, which shows the linear attenuation coefficients of tungsten and lead across an energy range from 100 keV to 20 MeV, which material do you think would result in a broader transmission penumbra for a 10 megavolt X-ray beam? Thank you for watching.